Hey folks, we are going to take the next step in the progression of this unit. Today we're going to talk about arithmetic series. Yesterday we talked about arithmetic sequences, and we're going to find out what series are in a moment. But for a homework you had this problem right here. The Drury Lane Theater has 25 seats in the first row and 30 rows in all. Each successive row contains one additional seat. How many seats are there in the theater? And again, the answer was 1,185, and I was interested in how you got that answer. I was hoping that you could find a way to do it without just adding up 25 plus 26 plus 27 plus 28, etc., all the way up to the 30th row, which would have 54 seats in it. So that's essentially the goal of the lesson. That's what an arithmetic series will allow us to do. So we will come back to this problem after we have developed a plan of attack. So these are our objectives for the unit. We want to understand what a series is. We want to develop a formula for calculating a finite arithmetic series. And we want to understand the divergence of an infinite arithmetic series. And again, those won't make total sense right now, but they will shortly. So let's get started. First thing I want you to do is find the sum of the first 5 terms of the sequence expressed right here. The sequence of terms that fit the form n squared, starting with n equals 1, which you can also write in sigma notation like that. Sigma is a Greek letter there. Notice we're saying that the form is n squared. We're starting at n equals 1, and we're continuing until n equals 5. So what this means is we are taking 1 squared, so equals 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. That is what that notation means, and then it wants us to actually add them up. So all we have to do is add those numbers together, and if you do so, you will get 55, just like that. That is essentially what a series is. A series is simply the sum of a sequence. So that was the sequence of terms that were squared. So 1 squared was the first term, 2 squared was the second term, 3 squared was the third term, etc., etc. And the series simply sums a sequence of numbers. So there you have it. Again, we can use sigma notation to represent a sequence. And what we want to do is come up with a formula to calculate the sum of arithmetic sequences. So we want to be able to calculate an arithmetic series. All right, well, let's look at this problem right here. We're going to say we have some sequence, a sub n, and we want it to be arithmetic. And we're told the third term is 54, and we're told that the ninth term is 18. So we need to figure out our common difference, d. We did this in our last lesson. So let's think about from 54 to 18, what's the difference between those two numbers? Well, the difference is 36, but from the third to the ninth, we are going down, so we should represent that as a negative 36. And what is the difference in the actual terms? That's the difference in the term values. What's the difference in the term numbers? Well, from 3 to 9, we are progressing 6 terms. So if we are moving 36 numbers between 6 terms, 36 divided by 6 is giving us negative 6 as our d value. So what can we do with that? Well, we want to find the first 4 terms and add them together. Well, we already know that the third term is 54 right there. If we want the fourth term, our common difference of d is saying all we have to do is subtract 6 from 54. So then the fourth term is going to be 48. Well, if we work in the opposite direction with the same logic, then the second term has to be 6 up. So we have to be at 60. And similarly, for the first term, we have to be at 66. That's a little example of where using a recursive formula can actually be easier than working through and finding the general formula. But at this point, we know the first term, we know the common difference, so writing the general formula would be pretty painless. But we don't need to. All we need to do now is add these numbers together. And when you do so, you get 228. So If it is a short series with only 4 terms like that, it's not too much work to add them up. But if we had a longer series with, say, 100 terms, we wouldn't want to add all of those together. So again, our goal is to develop a formula that will allow us to more simply add up a arithmetic series. But before we do that, we're just going to practice a few things. We want to take this series, which is again just the sum of a sequence. So that would be like our first term, a sub 1, our second term, a sub 2, a sub 3, a sub 4, a sub 5, etc., all the way up to a sub 6. So we have 6 terms, and we need to take this and we need to write the explicit formula for it. So for example, what's my common difference there? Well, from 4 to 7, I'm adding 3. From 7 to 10, I'm adding 3, etc., all the way up. So my common difference, D, is 3. My first term, a sub 1, is 4. So I can write my general formula, a sub n equals my first term, 4, plus my common difference, 3, times n minus 1, just like we came up with in our last lesson. Now to write this series in sigma notation, all we need to do is use the explicit formula a sub n, so 4 plus 3 times n minus 1. And now we need to essentially tell the sigma what parameters we want. And we want n to start at our first term, 1, and run up to our sixth term, 6. So that is all you have to do right there to write a series in sigma notation. Again, we're going from the first term to the sixth term, and we are just summing up our explicit formula. So let's try the same thing here again. Go ahead and pause, do this one by yourself. Think about what you need to do in order to know how many terms we have in this case, because we have an ellipses in the middle, which means there are an indeterminate number of terms being added between 13 and 41. So in a similar way, we have a sub 1, a sub 2, a sub 3, and we don't know what term value that last term is. So we're calling it a sub n. But what can we figure out? Well, we can still figure out that our common difference is 4. 9 minus 5 is 4. 13 minus 9 is also 4. So we have an arithmetic series here, and the common difference is 4. So let's write a general equation. So a sub n equals our first term, 5, plus our common difference, 4 times n minus 1. That would be our explicit formula right there. And let's use this a sub n term to figure out what the term number is. So a sub n equals 41. And then we have our explicit formula, 5 plus 4 times n minus 1. And we want to solve for n. So let's subtract 5 from both sides. 41 minus 5 is 36. So 36 equals 4 times n minus 1. Let's divide by 4 on both sides. 36 divided by 4 is 9 equals n minus 1. And so we can add 1 to both sides to get that. Oops, I wrote 10 equals 10. That's silly. N equals 10, which is telling me that this is the 10th term right there. So if I am using sigma notation to express this series, all I need to do is say start at n equals 1, continue until n equals 10, and I just need to give it the explicit formula, a sub n, which I've already found, 5 plus 4 times n minus 1, and that is all. And you could sum this, you could add them all up, but again, we're going to learn how to do that shortly. And to learn how to sum an arithmetic series, we're going to get a little story about a young man named Johann Karl Friedrich Gauss, born April 30th, 1777, died February 23rd, 1855. And this is an excerpt from the Wikipedia page. According to Isaac Asimov, Gauss was once interrupted in the middle of a problem and told that his wife was dying. He is purported to have said, "Tell her to wait a moment till I'm done." Wow, that is very absurd. I saw that and kind of felt like I had to include it in here. So I'm not sure what that says about this man. So if I were you, I probably wouldn't recommend being married to Gauss, but he was a pretty good mathematician, and he was very brilliant, and he came up with an ingenious way to make his teacher look like a fool. And that's the story I'm going to share with you now. So here's the story. When Gauss was a young lad in his school, the story says that his teacher didn't really feel like teaching anymore, and so decided to give the class essentially some busy work to keep them busy. That's what busy work does, to keep them busy so that the teacher could go off and do whatever he or she wanted to do, not interacting with the children. So the teacher said, all right, class, and this is, elementary school or, maybe even earlier than that. The teacher said, add up the first 100 numbers, the first 100 integers. So 1 plus 2 plus 3 plus 4, yada, 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 all the way up to plus 100. Notice I've also expressed that in sigma notation. Think about why that notation there works for this. Now, they did not have calculators at this time, and so the teacher thought that this would take them, a substantial amount of time adding all those numbers up. I imagine if you were doing it by hand, it would take a long time as well. But Gauss, being the brilliant young mind that he was, came up with, again, a very ingenious way to approach this problem. He looked at these numbers and he noticed a distinct pattern. So what I want you to do is I want you to pause this and I want you to think if you can notice a distinct pattern in these numbers. Try coupling them in a useful way. So pause it for a moment, see what you can do, and then I'll show you what he did. Okay, that's a long enough pause. So Gauss said, well, let's look at the first term and the last term, 100 and 1. If I add 100 and 1, I get 101. And let's look at the second term and the second to last term, 2 and 99. And if I add 2 and 99, I get that same number, 101. Let's add 3 and 98, the third term and the third to last term. Well, 3 plus 98 is also 101. 4 plus 97 is 101. 5 plus 96 is 101. And if you get all the way into the middle and take 50 and add it to 51, you also get 101. So each time you pair the nth number with the 100 minus nth number, you get 101. And think about it, if we're taking 100 numbers and we're pairing them up in groups of 2, how many pairs of 100 do we have? Well, we have 50 pairs of 50 pairs of 101, I should say. And so we are adding 101 50 times, which is the same as multiplying 50 by 101. And in that way, you can calculate this sum in a much, much simpler way than adding them all together. 50 times 101 is a lot easier to do than just adding up all the numbers by themselves. When you multiply those two numbers, you get 5,050. And so Gauss came up with this answer after just a few minutes and went up to his teacher and said, okay, I'm done, what next? And the teacher was like, no, there's no way you could have possibly done that, blah, 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 blah. And the teacher, I know everything. But apparently the teacher didn't know this. And so this basic idea here is actually exactly what we're going to do to calculate arithmetic series. So let's think about where these numbers are coming from. So first off, the 101, where is that coming from? Well, that is coming from the first term plus the nth term, whatever that last term we're adding up actually is. And where did that 50 come from? Well, that 50 came from the number of terms cut in half. And so that formula right there is our arithmetic series formula. And if you think about it, it'll work for any series. Think about a little example here. What if we do the series, say, 2 plus 4 plus, I can't do math, 2 plus 4 plus 6 plus 8. Well, then we'd be pairing up 2 with 8 and 4 with 6. And so 2 plus 8 is 10, 4 plus 6 is 10. How many terms do we have? 10 plus 10, well, we know that's going to be 20. Add them up yourself, you'll also get 20. But again, the 10 is coming from the first term times plus the last term. And if you think about how many of those 10s we have 2 coming from the total number of terms, 4 divided by 2. So 2 times 10 gets us 20. Add them all up, you also get 20, and there you have it. This would also work even if we're dealing with an odd number of terms. But again, don't take my word for it. Why don't you just try it real quick? What about the sequence 3 plus 4 plus 5? Well, first off, we know that that's going to be 12, but let's calculate that using the formula. So 3 plus 5, the first term, times the I keep saying that, the first term plus the last term, times the number of terms divided by 2. So 3 plus 5 is 8. So we have 3 halves of 8. 8 divided by 2 is 4. 3 times 4 is 12. So again, it works. Doesn't matter if it's even, doesn't matter if it's odd, doesn't matter what your common difference is. You're always going to have that connection since these are essentially linear functions. So let's go ahead and use this property now to answer the problem we started with. So let's come up with our recursive formula for this. So a sub n will equal our first value, which is 25, because our first row is 25 seats, plus our common difference, which is 1 times n minus 1 right there. And let's figure out how many seats there are in the 30th row. So a sub 30 is going to equal 25 plus 30 minus 1. So 25 plus 29, which gets us 54. I needed that so I knew what my final value was, a sub 54. And now I'm looking for the summation from n equals 1 up to n equals 30 for the 30 rows of this expression, 25 plus 1 times n minus 1. And I know that's clearly a silly way to write this, but just sticking with our routine here. So to do that, I am going to take the number of terms, 30, divide it by 2, and I'm going to multiply that by the sum of the first term, 25, and the last term, 54. And when you simplify that out, you do get 1,185, the number of seats in the theater. So then let's do two quick problems before I show you your homework. First thing we want to do is now use this new summation to find the sum of the first 1,000 negative numbers. And we want to express it in summation notation, sigma notation, and also find that sum. So think about what we're doing. If we're listing the first 1,000 negative numbers, well, the first negative number is negative 1, then the second is negative 2, the third is negative 3, blah, 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 etc., all the way up to the 1,000th negative number, negative 1,000. So if you compare this sequence to the actual term numbers, in each case, the number is just the opposite of the term number, which should make sense. So if I'm writing this in sigma notation, I'm going to start with my first term. I'm going to run until I hit my 1,000th term, and this is the opposite of my term number, so negative n. That would be the sigma notation for this sequence, for the series, the sequence where we want to calculate the series for it. And so then we can use our formula. We can say take half of the number of terms, so 1,000 divided by 2, and then multiply that by the sum of the first term and the last term. So if you calculate that, you should find your answer as negative 500,500. Now, if you weren't able to recognize the negative n, then all you need to do is say, well, I know I can write an arithmetic sequence as, or rather the explicit form of the nth term of an arithmetic sequence. I can express that as the first term, which would be negative 1, plus my common difference, which would be negative 1, times n minus 1. If we distribute that negative 1 in to both terms, we get negative 1 times n gives us a negative n, and the negative makes that a positive 1. So I have a negative n, a positive 1, and I have a negative 1 there, which cancels, simplifying down to the negative n, which is what we had. So let's do that, and then let's do this last one real quick. Whoops, that work's not supposed to be there. Ignore it. Okay. Well, let's find the sum of the infinite series right here. And you may be like, oh, I don't know how to do that. I don't know how to handle infinite series. But think about what this is saying. This is saying take 3 plus 6 plus 9 plus 12 plus all the other numbers in that series, so all these numbers that are continuing to increase by 3. Well, if we're adding infinitely many numbers together that are getting larger and larger and larger, that sum is itself going to be infinite. So there you have it. I could write it more explicitly in sigma notation, but I'm going to stop there for now. Here's your homework. 3 problems where I want you to express the series in sigma notation and also find its sum. Then 2 problems where I want you to calculate the nth partial sum. That's what this is saying right here. S sub n is the notation. That means calculate the nth partial sum. So for example, S sub 5 is saying find the sum of the first 5 terms. So a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. And you're doing the same thing for number 5. And then 6 and 7, I want you to try and express the series in sigma notation. Notice that they are not arithmetic series because they are not increasing or decreasing by the same amount each time. So my advice to you would be to write the term number underneath each term. So n equals 1, n equals 2, 3, 4, up, all the way up to that nth term, whatever it is. And look for a pattern that ties the term number to the number in the numerator, and look for maybe a different pattern that ties it to the denominator. And if you find that pattern, then express it as a quotient. This is on the website. See what you can do.